Humanity managed to conquer the skies just over a century ago, turning a fragile frame of wood and cloth into the most complex machinery on Earth. Today, hundreds of thousands of aircraft fill the sky daily, ranging from massive double-decker metal tubes cruising across continents to invisible supersonic jets designed for elite warfare. If you strip away the corporate branding and paint jobs, how exactly are these mechanical marvels classified? Before we decode the complex engineering of flight, a huge shout-out to our community here at the Explanation Hub. If you love pulling back the curtain on complex industrial engineering and the precise mechanics that keep the modern world moving, take a quick second right now to subscribe, turn on your notifications, and smash that like button. Today, we open a complete engineering and operational investigation into the sky to systematically explain every type of airplane. To understand how the global aviation ecosystem is built, we have to start exactly where every single pilot begins. General aviation. This broad category encompasses all civil aviation flights except for scheduled commercial airlines, classifying aircraft by their propulsion systems, weight, and operational environments. At the bedrock of flight training and private transport are single-engine piston aircraft like the iconic Cessna 172 Skyhawk or the Piper PA-28 Cherokee. These lightweight machines utilize a single internal combustion engine mechanically identical to a car engine to spin a fixed or constant speed propeller, optimized for low-altitude, short-distance regional flights. When a pilot requires more speed, payload capacity, and redundant safety over open water or rugged mountains, engineers add a second piston engine to create multi-engine piston aircraft like the Beechcraft Baron or Diamond DA-42, allowing the plane to maintain flight even during a catastrophic engine failure. When piston engines reach their absolute physical performance limits, aviation shifts to turbine power with turboprops. A turboprop uses a jet turbine core to drive a gearbox that spins a massive propeller, combining the raw efficiency of a jet engine with the incredible low-speed thrust of a traditional propeller. Workhorses like the Cessna Caravan, Pilatus PC-12, and the twin-engine ATAR-72 dominate this space as the ultimate machinery for short, rugged runways and regional commuter hops. As we scale up into pure jet propulsion, the machinery transitions into the elite world of private corporate transport, where business jets are built on a strict hierarchy based on range, cabin volume, and engine performance. Very light jets are essentially the entry-level sports cars of the jet world, weighing under 10,000 pounds. Aircraft like the Cirrus Vision Jet or the Embraer Phenom 100 are uniquely engineered to be flown by a single pilot while carrying 4 to 5 passengers on rapid regional trips under 1,200 nautical miles. Moving up the scale, light and mid-sized jets form the core workhorses of corporate fleets. Light jets like the Cessna Citation CJ4 offer expanded seating, while mid-size options like the Learjet 60 or Bombardier Challenger 350 introduce full stand-up cabins, high-altitude performance to fly entirely above severe weather systems, and cross-continental range. At the absolute pinnacle of civil engineering sit heavy and ultra-long-range jets like the Gulfstream G700 and the Bombardier Global 7500. Using incredibly powerful, ultra-efficient turbofan engines, these massive machines can cruise at Mach 0.90 at 51,000 feet, bridging cities like New York and Tokyo non-stop in complete luxury. When it comes to moving the masses via public transit, commercial airliners are divided into 3 distinct operational and structural categories. Regional jets, such as the Embraer E195 or Bombardier CRJ900, connect smaller local airports to major international hubs, typically seating between 50 and 100 passengers. These models utilize downscaled turbofan engines optimized for quick cycles, frequent takeoffs, and landing smoothly on shorter runways. Next are narrowbody aircraft, also known as single-aisle airliners, which form the absolute backbone of global domestic air travel. Driven by highly efficient, high-bypass turbofan engines, the Boeing 737 and Airbus A320 families carry between 150 and 240 passengers, focusing purely on economic optimization and maximizing fuel efficiency per passenger mile on short to medium-haul routes. Finally, wide-body aircraft are the heavy giants of intercontinental travel. Featuring a twin-aisle configuration, these massive structures are engineered to handle the staggering physical stress of ultra-long flights. The twin-engine Boeing 777 and Airbus A350 use the largest turbofan engines ever built to haul up to 400 passengers across oceans, while four-engine double-decker anomalies like the Airbus A380 represent the absolute limits of traditional aerodynamic scaling. Not every airplane is built to carry everyday passengers or standard cargo. Some of the most fascinating engineering in aviation belongs to special mission aircraft designed for highly specific physical environments, while standard cargo planes are simply converted airliners. Purpose-built military and industrial logistics giants like the C-17 Globemaster or the Lockheed C-5 Galaxy are engineered completely from scratch. They feature high-mounted wings, so their giant engines do not ingest debris on unpaved runways, rugged multi-wheel landing gear to distribute extreme weight, and massive nose or tail ramps for loading heavy armor and machinery. Similarly specialized are amphibious aircraft and seaplane designs engineered with specialized hull shapes or massive floats to land directly on water. The Canadair CL-415 is a legendary firefighting super scooper designed to skim a lake surface, ingest over 1,600 gallons of water into its internal tanks in just 12 seconds, and immediately take off to fight raging wildfires. Finally, we cross into the bleeding edge of aerospace engineering, military warplanes. Global militaries categorize these platforms with a strict tri-service designation system that instantly defines an aircraft's mechanical purpose. Fighter aircraft like the F-22 Raptor are engineered exclusively for air-to-air dogfighting and establishing absolute air superiority, prioritizing thrust-to-weight ratios greater than 1:1, extreme maneuverability via thrust vectoring nozzles, and advanced stealth radar cross-section reduction. Attack aircraft like the iconic A-10 Thunderbolt II, are built for low-altitude close air support to hunt enemy ground forces, acting essentially as a flying titanium bathtub. Wrapped around a 30mm rotary cannon built to survive intense ground fire. Bomber platforms are massive. Heavy strategic platforms designed to carry massive payloads deep behind enemy lines, ranging from the high-altitude, long-range B-52 Stratofortress to the flying wing stealth design of the B-2 Spirit. For communication and surveillance, special electronic aircraft like the E-3 Sentry AWACS are modified with massive radar radomes to act as a flying command center, coordinating entire air theaters from the sky. Lastly, tanker aircraft like the KC-46 Pegasus function as flying gas stations. These heavily modified airliners are engineered to transfer thousands of gallons of fuel mid-air to thirsty fighters and bombers, extending global military reach indefinitely. In conclusion, every single aircraft in the sky is a masterclass in physical compromise. To get more range, you need more fuel, which requires bigger wings, which creates more drag, requiring more massive engines. The entire history of aviation is simply the story of engineers balancing this delicate physical equation to push humanity further and faster through the air. Which category of aviation engineering fascinates you the most? Are you a fan of the sheer mechanical scale of wide-body airliners, or does the raw, high-G performance of military stealth fighters catch your eye? Let us spark up a discussion down in the comments. If you enjoyed this comprehensive breakdown of flight machinery, please smash that like button right now to help push this video into the algorithm. Share it with a fellow tech or aviation enthusiast, and subscribe to the Explanation Hub so you never miss an episode when we pull apart the world's most incredible physical systems. Thanks for hanging out in the workshop with us. Stay curious, and we will see you in the next breakdown.